All right, page 109, problem 7 was your homework. And we began looking yesterday at solving skewed vectors. And again, skewed vectors, they're not going to run in line with each other, either parallel or anti-parallel. They're not going to be at right angles with each other, so where the Pythagorean theorem's out the window. So for these skewed vectors, I said when you draw the primary vector, whatever it is, and you draw the secondary vector, whatever it is, they're going to be at weird angles to each other. Of course, we start the secondary vector at the head of the first, and then we go from start to finish for the resultant, just like we would have for the right triangle, Pythagorean theorem, perpendicular vectors. But what kind of triangle is formed by skewed vectors, Audrey? An oblique triangle. And to solve an oblique triangle, we don't use Pythagorean theorem, we don't use arctangent, we use two laws instead. One of them, Kendall, is called the law of cosine. The law of cosines. And what is the law of cosines, Kendall? Starts out a lot like the Pythagorean theorem.
C squared equals A squared plus B squared.
That's where it changes.
Minus 2AB.
Just remember the law of cosines.
Cosine of something of C squared.
Well, no, just the C, sorry, yeah. So whatever the letter that's over here, it's going to be that one. By the way, if you look at the wall, and those in pre-cal, we'll use that poster later. You notice in that problem, the law of cosines is set up with the A squared. But notice the pattern equals B squared plus C squared minus 2, and then whatever letters are here are the letters that appear here, and whatever angle matches up with this one is the angle that goes there. So you can write it actually 3 different ways. You can solve it for A squared, B squared, or C squared. This is the way we will use it, since we're assuming, like we did before, that the C is the resultant. All right, and then that's going to give us the magnitude of the resultant. It's important to remember that once you find C, put it in the memory of the calculator, because you're going to need it to find the direction. Now, we have an intended direction, and then we have what ends up actually happening. So we have the ideal, and we have reality. And they're going to be just a little shifted off of each other at some angle theta. But to find this angle, we need another law. This time,
law of sines.
Law of sines. And what is the law of sines?
B over sine of B equals. Do you want the whole thing or just the part?
Yeah, whatever.
Oh, so A over sine of A equals B over sine of B equals C over sine of C.
There we go. Now, realistically, the way we're going to end up doing them, we only really need the last 2 parts. Later on, when we get to solving oblique triangles in pre-calculus, where we're solving the triangle itself, we'll need to use all 3 parts. But for now, we're just finding with this angle here. And of course, this angle will end up being angle B, since we're calling B, or we're designating lowercase b as our secondary vector. Of course, angle capital C will be the angle that's actually between the primary and secondary vectors. And so the angle right here we really don't care about, and so we won't end up using the primary vector A in the calculation. Again, this is going to be the memory value, whatever that happens to be. So really the key to all of it is you've got to draw a good picture. I mean, you need a good picture with perpendicular vectors. You really need a good picture with skewed vectors, because you won't know what the angle is. Sometimes the angle they give you is the angle. Sometimes you have to find the supplement. Sometimes the complement. Sometimes you have to add 90, right? We looked at all 4 ways you could see it. So the picture is everything. Read problem 7 for us, if you would, Audrey, and let's see how our picture should have looked.
An ocean liner heading west at 25 kilometers per hour comes into a current of 15.0 kilometers an hour, directed 30 degrees north of east. Find the new velocity of the liner.
All right. So the primary vector is the
ocean liner.
The ocean liner. It's in his intended direction, right? He's intending to go west. So we're going to draw our primary vector like that. Did we get our primary vector correct? All right, now for the secondary vector, because it's at a weird angle. It's, well, not super weird, but it's north of east. Class, where's east? Where's north of east? So 30 degrees north of east. We should have a vector coming off something like this and a 30-degree angle here. Did we have those 2 vectors? All right, then you have no hope of getting it right. If you botch the picture, you are doomed completely. It's just the sad reality. All right, did we finish the triangle by putting the resultant here, U2? All right, so Audrey will be working along with me. U2 should be fine. So our secondary vector was 15 kilometers an hour. The primary vector was 25 kilometers per hour. Obviously, we understand ocean liners to measure things in knots, not miles per hour, but whatever, okay? We're going to be flexible. We're going to use terms that we understand, or in this case, kilometers per hour. So we need to, first of all, find the magnitude of the resultant. Correction. First of all, we need to find the angle between the vectors. What is the angle between the vectors, class? 30. This time it really is 30. We didn't have to do any calculations with the angle, as we often will. This time we did not, though. And so when we set it up, again, assuming that this is A, this is B, and the resultant is C, we're going to set up our law of cosine. Say it with me, class. C squared equals A squared plus B squared minus 2AB times the cosine of C. And remember, for you indirect entry, actually I think all of you will need the parentheses there. Indirect entry people will hit the equal sign, and then at the end, the square root symbol. Michael, in your case, you can put the square root first and just end with the equal sign. So same number of keystrokes, but we just put our square root at the end. So Audrey's doing this with me. You two should already have this done. We've got a 25 squared plus 15 squared minus a quantity. 2 times 25 times 15 times 30 cosine. Close the parentheses, hit the equal sign, take the square root. And ocean liner was trying to go 25 kilometers per hour. This current's kind of getting in the way, isn't it? Slowing it down. So how fast does ocean liner actually wind up going, Audrey? Only about 14 kilometers per hour. Now, it's not exactly 14. It's 14.159, blah, blah, blah. So it's important to put it, class, in the memory. All right. And then we're going to use that in the law of sines, which is, class? A over the sine of A equals B over the sine of B equals C over the sine of C. Again, we're going to lock in on the last two. B is the secondary vector, class. Secondary vector, 15, over the sine of the angle B. That's the theta that we're solving for. That's what we want. Equals C, which is going to be our memory value, 14.1, blah, 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 over the sine of angle C, which is always the angle between the two vectors, 30 degrees. So we'll start by cross multiplying here, 15 times the sine of 30. Divide out the memory value, and then take the arc sine or second function sine at the end to get our angle. And if it looks kind of isosceles-y to you, well, it says 15 and 14 are pretty close, and these angles turn out pretty close also. What is the angle, class?
32.
At 32 degrees, so almost isosceles, 32 degrees. Now again, where was the ocean liner trying to go? West. Where was the ocean liner pushed?
North.
A little bit northward, right? Pushed a little off course to the north of west. Did you two have that answer? Yes?
I had the first part, but not the second part.
Not the second part. Go with, well, you'd have to put it in the memory of the calculator to get it exactly. But tell you what, let's go with, just go with a 14.159 instead of the memory. Redo the law of sines using 14.159 instead of memory 1.
How do you plug it in?
What's on your calculator right now?
0.9 something.
Okay, so remember, if you wanted to write it out, Kendall, we would say M1, or memory 1, times the sine of B equals 15 times the sine of 30, right? Or we can use parentheses instead of the raised dot so we don't confuse ourselves with a decimal. All right, so to get sine of B by itself, we would divide away the memory value, or in this case, you're going to do a 14.159. So 15 times the sine of 30, or 15 times 30 sine equals
7.5.
Then divide by memory, or rather divide by 14.159 equals, and you should have a little bitty decimal. All right, the little bitty decimal point, 5.1, I think, something blah, 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 that's the sign of b. But since I don't want the sign, we're going to take the arc sine of both sides. So that's the last thing you'll do is a second function sine. And there will be your angle of about 32 degrees, 31.9 blah, blah, blah degrees. All right? On your paper, go and jot down this information. Let's suppose that Michael is at camp. They're having an archery contest, and the target is exactly downrange is exactly due north from where Michael's standing. So Michael aims an arrow exactly due north, and when he releases the arrow, it flies from the bow with great speed at 60 miles an hour. All right, so the arrow leaves his bow at 60 miles an hour, going due north. Right as Michael goes to shoot, however, a wind blows out of the east at 10 miles an hour. A wind blows out of the east at 10 miles per hour, which causes him to hit the target next to his, thus winning the competition, winning for his opponent. Anyway, it's bad luck sometimes. All right, so the wind blows out of the east at 10 miles per hour. At your seats, find how fast his arrow really flies and the direction. So in other words, find the velocity of his arrow. Shoots the arrow north at 60 miles an hour, but right as he shoots, the wind blows from the east at 10 miles per hour. Find the resultant velocity of the arrow. Is the picture correct? All right. Are we going to need to use the law of cosines? No, because they're at right angles to each other. What can we use instead? Pythagorean theorem. Good. Let's assume it's a 10 point and a 60 point, because one sig is sad. What is the magnitude of the resultant, class?
61 miles per hour.
Yeah, 60.82, blah, 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 rounded 61 miles per hour. So his arrow actually speeds up just a nudge, not much. It's negligible. You wouldn't notice a speed up. What you will notice is that it gets blown off course. What angle off course does it get blown by the wind, class?
9 degrees.
Well, if we go 2 sig figs, 9.5 degrees, 9.46, blah, 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 but 9.5 degrees. Now, he was intending the arrow to go north, but this wind out of the east pushed his arrow to the west of north. Questions on this? I want to make sure we don't forget how to work the easy ones, the perpendicular vectors. Did we get this? All right, no questions on Pythagorean theorem, arctangent. All right, well, let's continue working with the time we have left on skewed vectors. I have a handout for you. And of course, if you're watching on YouTube, it is in the description of the video as always. You may have room to work right here on the handout. If you want to work on another sheet of paper, that's fine as well. The picture, of course, is of utmost importance. So on number 1, I want you to read it, figure out the picture, and don't do anything else, just the picture. Get your picture on that first problem. A ship is crossing the Atlantic Ocean going due west at 32 miles per hour. A 12 mile per hour wind comes out of the north at an angle of 20 degrees to the south of east. Find the ship's resultant velocity. Did you get the picture? The ship is going west. There's our, 35, not 13. I get 13. There's our ship. Then it says the wind comes out of the north, so it's going downward, right? But it's not a perfect north wind. In fact, it's kind of blowing southeasterly, right? 20 degrees to the south of east. So it's actually more of a west wind, honestly, than a north wind. But it's not going east, but 20 degrees to the south of east. So there's our picture. Correct the picture and solve. Correct the picture and solve. Once you get the magnitude, check against the board. Make sure you've got it right. If you're good, continue on. If you're not, you got to fix it because otherwise you're doomed to mess up the next part. Once you've got the angle, check the angle. And finally, the direction. Okay, Audrey's got it. Michael's got it. Kendall's got it. All right. Questions on this? Let's go to the next one. Plane is flying due east at 240 miles an hour. Wind is blowing 35 degrees to the north of west at 30 miles an hour. Find the resultant velocity of the plane. Let's start with just the picture. All right, check the picture. Here we have it. Airplane's going east, that's this way. The wind isn't blowing west, it's blowing to the north of west. So start at the last one mentioned, start at west, but then go 35 degrees north. And that's where we're at. All right, fix the picture if you didn't have it and solve. Fix the picture if you didn't have it and solve. Once you get the magnitude, check your answer before you go on to the direction. You've got it, check your answer. If you need help, raise your hand. Michael's looking hard at something. What'd you have?
I had 6.5 degrees.
But you had the correct 216.11?
Yes.
Did you use 216.11 or did you use 220?
I used 216.11.
Okay, so you said that 30 over the sine of b equals memory, which is the 216.11 over the sine of 35. So you multiplied 30 times the sine of 35?
I may have done sine of 35. No, sine of 30 times 35.
Oh, okay, so you got the angle of, you said 35 times sine 30 instead of 30 times sine 35. You just got the two numbers mixed up. Okay, and that explains why you'd be that little bit off. Okay, questions on that one? All right, on number 3, start with a picture. Don't do anything else, just the picture. By the way, which one's going to be primary?
The second one.
The second one listed, right? So you can't say, well, first one's listed primary. No, here, the wind is mentioned first, but that's definitely secondary. Primary is what's intended, which is the actual throwing. So on a day the wind's blowing 5 miles per hour, 15 degrees to the south of west, a boy throws a paper airplane 6.5 miles per hour due south. Find the resultant velocity. And this one's actually a little bit more realistic because we don't necessarily have the streamlining and the natural inertia and momentum the same way we would the others. We're like, well, theoretically, yes, the math works, but realistically, it wouldn't quite be that way. Here, it probably pretty much would, with the minimal mass of the paper airplane. All right, check your sketch. Did we get it? All right, so the boy going 6.5 south with his airplane, right? The wind, though, is not quite west. It says 15 degrees south of west. So this would be west, and you see a little dotted line, not west, 15 degrees to the south of west. So question, what's the angle? It's not 15. 105, because we have to add the 90 that they would have been plus the 15 more. So we really have a 105 degree angle we're using here. Questions on the picture? All right, go from there. as before, once you get your magnitude, check it. If you're good, move on. If you're not, figure out what you did wrong. Audrey's got it, Kendall's got it, Michael. Double checking some things. What did you have, or what do you have? Did you get the magnitude, the 9.169?
No, I forgot to square it.
Oh, okay, so you've got to square the 6.5 and square the 5. Okay, yeah, that would do it. All right, any questions on that? What was your magnitude then? It must have been small.
It was like 5.6.
Gotcha, yeah. And of course and that's where the picture helps too, because notice the resultant appears longer, right? In fact, with the angle, it must be the longest. So if you get a 5.7, you're like, wait a second, this plane shouldn't have slowed down. What happened? And that's one way when you're not just, okay, I'll look at the board and see if my magnitude's right. You kind of figure out, does this make sense? No, it doesn't. And so go from there. All right, we got time for one more, and we'll save the last one for homework, but let's take a look at number 4 next. Ocean liner heading north, 22 miles an hour, comes into a current 13 miles an hour, 56 degrees west of north. Find the new velocity. Check your picture. All right. You got the boat going north, right? It's the whole west of north thing, right? Start at the second direction. Start at the north and then go to the west 56 degrees. Go 56 degrees west side of north. Did you start at the west and try to go 56 north? Let me see the picture. The rest of you go ahead and get started. I want to see the picture.
I went that way.
Oh, okay, that's east.
Yeah.
So what you do on your paper is you do north, south. You go wee, and just keep it there for reference. All right. So what is the actual angle, class?
124.
Yeah, we got 124. Did you get that? We all good on the 124? Not good on the 124. Okay, so fix it and kind of have to redo some calculations. All right, because we see, Kendall, that the 180 would be if it had been straight north, right? But we came 56 degrees off of that 180. So we're not adding 56 to 90. We're taking 56 from the full 180. All right, so go ahead and redo the calculation then in that case. All right, I want to go over the last one with you. You're going to do it for homework, and there's a little sketch there to help you out, because this one's kind of weird. Notice the first four all have the initial intention, due north, due south, due east, due west, right? And then the after effect was the one that was kind of off kilter, so to speak. Look at this one. A man tries to paddle his kayak across the Nile River 6 miles an hour at an angle of 20 degrees to the north of west. The Nile River flows from south to north. So the primary vector here is the goofy one. So I actually started kind of with the north, south, east, west, and he's going 20 degrees to the north of west. So the primary vector is this one. Does that make sense? But then the Nile River is due north. So there's the secondary vector. Do you see it on the picture? Now, just watch for sake of time. If I were to draw a little parallel right here, we would have alternate interior angles of 20 and 20, correct? So what will be the angle between the vectors? I have a right angle here, plus I have this little alternate interior 20-degree angle, correct? So we've got a total of a 110 between the vectors. Now here's the only other glitch. When you find the resultant, right, we always define the resultant as north of west, north of east, east of south, whatever, right? Your angle theta, class, isn't going to be based on north, south, east, or west. So you're going to have to tack on an extra 20 to it so that when you mention your angle, you are describing the resultant's velocity based on west. Because you can't base it on something that isn't north, south, east, west. Does that make sense? So a lot of interestingness going on there in this problem. Problem 5 for homework. We'll take a look at it next time as we wrap up perpendicular and obviously now skewed vectors. All right, when the bell rings, you'll be dismissed, and have a wonderful rest of your day.